Okay, magnetic forces on current carrying wires. We've already seen that when a charged particle is in a magnetic field, it experiences a force given by F equals Q times B cross B. And so if we have a current carrying wire, we have charged particles in that wire, they would also experience a force like that. So we can say that if we have a current carrying wire, we can say that a charge in that wire would experience a force. So if we have a current carrying wire, a charge in that wire will experience the force given above. And so we can use that. So let's consider current carrying wire of length L. So we're going to take a current carrying wire of length L. And let's say that charges move with velocity V in this wire. So this is current I. And we say this is the length L. And so the charges are moving. A charge Q is in here, moving with a certain velocity V. So we know that a charge in a magnetic field, a charge experiences a force F equal to Q. And so we can say the current is given by the charge per unit time. Delta T is just equal to the length of the wire divided by the speed. And we can say the current is equal to Q L over V. So delta T is L over V, so it's going to be Q. This is L and V at the top. Q. So we replace Q in the formula for force to get F equals I times L over V times V cross B, like that, which can then be written as I times L cross B. We've just cancelled out the force on a wire, or on a current carrying wire of length L is given by F equals I times L cross B. And that force is going to be perpendicular to the wire itself. It's going to be perpendicular to the plane of the wire. F is perpendicular to L, and so that's the force that's what we shall use for force on a current carrying wire in a magnetic field. Any questions at this point? Okay, so let's look next at the force between parallel wires, force between two parallel wires. So let's take a wire carrying a current I1 and the second wire carrying a current I2. At some point, we shall make the currents the same. So what we have is, so we have the two wires carrying current I. By definition, we know that whenever there's a current carrying wire, there's a magnetic field around it. So let's take the top wire. So we can say that for top wire, the field at I2 is into the board. I'll explain to you shortly how that is. So for top wire, the field at I2 is into the board. And then we can say that for bottom wire, the field at I1 is out of the board. And so the wires, let me see, we can take the distance between them, and let's take the length to be L1 for the top wire, and the length to be L2 for the bottom wire. So these are the wires. This is the wire itself carrying current I. Okay, so by right hand rule, if I grab the bottom wire with my right hand, so we can use our formula. So we can say that using F equals I L cross B, we can say that F1 is the force of 1 on 2. Let F1 be the force of 1 on 2. Let me do it. Let me rewrite this. Actually, this is fine. We shall say let F1 of 2 be the force from the field of I1 at I2. And we shall say let F21 be the force, the field from the field of I2 at I1. So let me redraw this for you so you can see what I'm saying. So this is I1, I2. I1 has length L1, L2 has length L2. The distance between them is D. Okay. So we know that we know B of 1 is equal to mu naught I1 over 2 pi d. The magnetic field of 2 is mu naught I2 over 2 pi d. Okay, so the field of 1 at point 2 is mu naught I over 2 pi d, and the field of 2 at point 1 is mu naught I2 over 2 pi d. Okay, so the currents are this way. So the current of 2 at 1 is going to be this current, this field. 2 at 1 produces this field. So this is the field at 2 at 1, or field of 2. And then the field of 1 by right-hand rule is going to be into the board at this point. So this is the field of 1, which is into the board at that point by right-hand rule. And so the force then will be this. So at this point here, at 1, the magnetic field of 2 is out of the board. Okay, it's coming out at you, and the current is to the right. So the force is going to point downwards. So this is the force of 2 on 1. And then at the bottom, the field is out of the board. The field is coming, no, the field is into the board at 2. And the current is to the right, so the force is upwards. So this is the force of 1 on 2. So the force F is equal to I, L, B, since L and B are at right angles, using that to mean perpendicular to B. Okay, so this symbol means perpendicular. Which label?
F1 and F1, 2.
The force of 2 on 1 and the force of 1 on 2. I think the labels are fine.
Oh, yeah.
Yeah, I think they're okay. So the force of 1 on 2 is equal to, the force of 1 on 2 is equal to the current in 2, length of 2, and the field of 1. Okay, that means make sure that I got that right. The force of 1 on 2, current in 2, length of 2, and field of 1, that's right. And then the force of 2 on 1 is equal to the current in 1, length of 1, and the field of 2. And so force of 1 on 2 is equal to I2 L2 B1, which is mu naught I1 over 2 pi d. And the force of 2 on 1 is equal to the current in 1, the length of 1, and the field of 2, which is mu naught I2 over 2 pi d. So we see that the force of 1 on 2 is equal to mu naught I1 I2 L2 divided by 2 pi d. And the force of 2 on 1 is equal to mu naught I2 I1 L1 divided by 2 pi d. So we can say that if L1 is equal to L2 and equal to L, and if the currents are equal, I1 equals I2 equal to I, then we can say that the force of 1 on 2 is equal to the force of 2 on 1, and that's equal to a certain force F between them, and that can be written as mu naught I squared, we can do I squared, over 2 pi d, mu naught I squared L over 2 pi d. Currents are not equal, then you can write F, the force between them is just equal to mu naught I1 I2 L over 2 pi d. So suppose they have the same length but an equal current, then you have that. So if two wires carry the same, if two wires are carrying currents in the same direction, they attract each other. If they are carrying currents in opposite directions, they repel each other. So what we found out is that if two wires carrying currents in the same direction, they attract each other. If they carry currents in opposite directions, they repel. Any questions on that so far? And then we can finish with the force on forces and torques on current carrying loops. So let's finish with that and then we'll be done. Torques on current loops. Okay. So if we place a current loop in a uniform magnetic field, if we place a current loop in a uniform magnetic field, we can analyze. So let's say we have a uniform field. Let me draw the loop like this, and then I'll draw the magnetic field this way. Okay, so let's see how that works. So we'll draw the magnetic field that way, and so this is carrying a current going this way. Current is going down that way and going this way. So we can assume that this is free to rotate about an axis. This is the axis. So let's see how that works. So this is pointing, this is at a plane. So we'll see how that works. So let's say that since this is a current carrying loop, it will have a dipole moment mu, which points this way. Okay, and my drawing is not the best, but let me see if I can. I think this should go like that. So we have a current carrying loop that way. Okay, so this is an angle theta. So we know that, let me rewrite that better, maybe you can see that. So it's a current carrying loop in a uniform magnetic field. We know that a current carrying loop is a magnetic dipole. So we'll use that at the end. But let's first of all analyze it from the point of view that it's just segments of wire in a magnetic field. Okay, so we know that the force on a segment of the wire, or we know that the force on a wire in a magnetic field is given by F equals I L B. And so if we think of a segment at the top, or let's say we have a segment, at the top, the current is going this way, the field is this way. Let me see if I can, yeah. So the field is coming this way and the current is this way, so the force is upwards at the top. Okay, so the force here is going to be like that. And then at the bottom, the current is going this way, the field is that way. The field is that way, so the force is downwards over here. So the tendency is to cause a torque on the wire to rotate it. Okay, so we'll say that this is the force at the bottom, force at the top. Okay, the forces on the loop are Ft and Fb. F is lowercase b, so the force on the bottom segment is F subscript b. We can say these forces will cause the loop to rotate. So one of them is on top and one is at the bottom. So the loop is going to rotate in the same direction. It's going to rotate in a clockwise direction. Okay, that's a clockwise direction. So we can say that the torque, so the loop will rotate in a clockwise direction with a torque given by torque net will be equal to torque at the top plus torque at the bottom, or torque due to the top force and the bottom force. So this is going to be equal to, the torque at the bottom is going to be equal to the lever arm, which is the lever arm there is going to be L over 2, because the sides are length L over 2 times F sine theta plus L over 2 F sine theta. So F bottom, F top, where L is the length of a side of the loop. And so I take L over 2 because it's rotating about an axis through the center. So if the sides are all of length L, I don't want to draw too much in here because it becomes messy. But you can see that if the sides are length L, then if it rotates about this axis, then the lever arm is L over 2. Okay, so it's becoming too messy now with too many lines in there. So let me draw it here now. So what we have is something that looks like that. So the axis is this way, and this is a square loop, so we can say this is the length L. So half of that is just going to be L over 2. Okay, so this is half of it is L over 2. So it rotates about its axis. So the force is this way on there, and the force is that way. So F bottom and F top. Okay, so the net torque, the torque is equal to R cross F. which is the same as L over 2 cross F. So torque at the top, L over 2 cross F top, and the torque at the bottom is equal to L over 2 cross F bottom. Okay, so that's why I ended up with what I had up here. So the net torque is just going to be equal to 2. Let me do it this way. Let's assume that the forces are equal. Okay, so assuming the forces are equal, so we can say that since the same current is flowing, we have F equals I L B again. Okay, so the force is equal to I times L times B. So we can say net torque is equal to, what did I have up here? L over 2. So we can say L over 2, and then another L times I times B sine theta plus L over 2 times L times I B sine theta. So net torque can be written as, so if you add these two together, we're just going to have L squared I times B sine theta. So I've added L over 2, L squared over 2 IB sine theta plus L squared over 2 IB sine theta. That just gives us L squared IB sine theta. Because I have two halves, I'm just adding them. Okay. Note that L squared is equal to the area of the loop. L squared is the cross-sectional area of the loop. So we can say the net torque is equal to I times the cross-sectional area times B sine theta, where we can note again that the current times the area of the loop is equal to the dipole moment mu. Okay, this is dipole moment. Okay, so we can replace that now and say the net torque is equal to dipole moment times B sine theta. And since mu B are vectors, we can write that we have that the net torque is equal to mu cross B. Okay, so the net torque is a vector, so the torque on the current carrying loop in a magnetic field is just equal to the dipole moment crossed with the field B. Any questions on that? So it's mu cross B, dipole moment is B. Okay, so mu is the letter mu. Okay, it's the dipole moment. Any questions on that? Okay, so this is used in the electric motor. This is the principle of the electric motor that we've been seeing all around us. If you take a loop and you put it in a magnetic field with a current going through it, we have the batteries that will show that there's a torque on it which causes it to rotate. All right, so when you do a project where you are doing the electric motor, make sure you include a formula like this in there showing the torque on the current carrying loop in the field. This is the principle of how it works. So we include the torque on it and the dipole moment and all that. Okay. Okay. So this is where we shall end.